Booster 18 didn't just fail at Starbase. It literally unzipped like a zipper running down stainless steel. The images coming out of Massey's test stand show something engineers rarely see, a complete structural tear that spread across multiple rings, peeling the booster open like wounded metal petals. SpaceX is already scrapping the remains, but the tear pattern reveals critical data about how their steel reacts under extreme stress. What caused the initial failure point at the base, and why did it propagate so catastrophically upward? Let's dive right in. The scrapping operation at Starbase tells a story written in torn steel. When SpaceX's crews rolled Booster 18 off the test stand, what remained was barely recognizable, just a few bottom rings still intact, with the rest reduced to jagged metal sections being loaded onto transport stands. The most striking feature wasn't what was left, but how it failed. The tear pattern shows a clear origin point at the base, near where the booster connects to the test stand, and from there, the failure propagated upward in an almost surgical unzipping motion. What makes a failure pattern this clean, and what does it reveal about the stress loads during testing? Here's where it gets technical. The COPV, that's the composite overwrap pressure vessel visible in the wreckage, sits exposed like an autopsy revealing internal organs. These spherical tanks normally hide inside the booster structure, storing helium at incredibly high pressures to help pressurize the main propellant tanks. Seeing one intact amid the carnage confirms SpaceX properly depressurized the system before scrapping began, but it also provides a rare glimpse at how these internal systems survived while the outer structure catastrophically failed. The COPV remains pristine while the steel around it peeled away like paper. Does this suggest the failure was purely structural, originating in the steel itself rather than from internal pressure events? The wound pattern deserves closer examination. Engineers describe it as the root of the tear, that initial failure point at the booster's base where maximum loads concentrate during testing. From there, you can literally trace how the failure propagated, starting narrow, widening as it climbed, then folding outward in those petal-like formations that made the original video go viral. The cut marks from SpaceX's crews appear alongside the tear patterns, showing where they had to assist the separation versus where the steel simply gave up on its own. This isn't random destruction, it's a failure with a story, one that starts with a single point of weakness and cascades into total structural compromise. What was that initial weakness, and could it have been predicted? Rain fell on the wreckage during transport, and those water droplets rolling down the torn stainless steel created an almost artistic effect. A reminder that this isn't just scrap metal, it's 304L stainless steel that cost millions to manufacture, assemble, and test. Each ring of this booster represented precision welding, quality control checkpoints, and engineering decisions made months ago. Now those decisions are being reverse engineered through failure analysis. SpaceX isn't wasting this disaster. They're mining it for data, every tear pattern, every stress concentration point, every weld that held versus those that didn't. All of it feeds into the design improvements already being implemented on Booster 19 and beyond. And here's what most coverage misses: the new hot staging ring section sitting among the wreckage. This wasn't the old style ring. This was an updated design, part of SpaceX's continuous iteration process. The fact that it survived relatively intact while the lower structure failed provides crucial comparative data. The hot staging section experiences some of the most extreme thermal and mechanical loads during flight. Super hot exhaust gases, rapid pressure changes, violent vibrations. Yet it held together while the base structure unzipped. What does that tell us about where the real engineering challenges lie in these boosters? SpaceX's response has been methodical and swift. Within days of the failure, transport stands were rolling in, cutting crews were sectioning the wreckage, and everything was being hauled to the scrapping area behind the Starship assembly facility. But notice what's happening simultaneously at Massey's test stand. They're already preparing for the next test campaign. New hardware is arriving, cryo testing continues, and the infrastructure that witnessed Booster 18's demise is being prepped for its successor. This isn't a setback causing delays. It's data collection happening in parallel with forward progress. How does SpaceX maintain this pace while learning from failures that would halt other programs for months? The Gigabay construction in the background adds another layer to this story. While Booster 18 was being dismantled in the foreground, massive steel beams were being lifted and welded into place for the new production facility. This visual metaphor, destruction and construction happening simultaneously, captures SpaceX's entire philosophy. They're building the factory that will build better boosters, informed by the failures of current boosters, all while testing the next generation. The welding sparks flying at night, the overhead cable work, the precision beam placement, it's all happening within sight of where Booster 18 met its end. Ship 39 stands in stark contrast to the carnage, representing what success looks like. The heat shield tiles are pristine, arranged in their characteristic hexagonal pattern, with those smaller decorative tiles creating visual distinction. This ship is nearly ready, a testament to SpaceX's ability to produce flight-ready hardware, even while processing dramatic failures. The reflection of the Gigabay construction in Ship 39's polished stainless steel creates an almost surreal image, the future literally reflecting off the present. But what specific improvements from Booster 18's failure are already incorporated into Ship 39's design? Booster 19 is where the lessons get applied. The transfer tube sections, massive pieces of hardware nearly the size of a Falcon 9, were rolling in during the same period Booster 18 was being scrapped. These aren't just replacement parts. They're improved components incorporating data from every previous test and failure. The manufacturing precision required for these transfer tubes is extreme, with tolerances measured in fractions of millimeters across structures dozens of meters tall. SpaceX is essentially building Booster 19 in the shadow of Booster 18's failure, each weld informed by what the tear patterns revealed, each structural reinforcement placed based on where the previous design proved insufficient. The pad infrastructure work adds urgency to the timeline. Pad 2's chopstick arms were being rotated, maintenance hoods removed and reinstalled, deluge systems tested, all the preparation work for catching a returning booster. The irony isn't lost. They're preparing to catch boosters that will be built with lessons learned from a booster that unzipped on the test stand. The cable chains protecting the chopstick electronics snake up and down the tower. A reminder that catching a 250-foot-tall rocket booster requires systems within systems, all working flawlessly. Meanwhile, Pad 1 is being completely demolished and rebuilt, jackhammers tearing up the old foundation to make way for upgraded infrastructure. What specific weaknesses are they addressing in that rebuild? Over at the ASU, the ambient storage unit, something unusual happened that further illustrates SpaceX's iterative approach. Fresh concrete was poured with insulation panels embedded, but then crews came back and demolished sections of it, rebar sticking out at odd angles. Measurement error? Design change? Specification revision based on new data? Whatever the reason, SpaceX doesn't hesitate to tear out completed work if it's not right. This same philosophy applies to Booster 18. When something fails, you don't cover it up or minimize it. You dismantle it, study it, and build better. The massive turbo pump being delivered to the ASU, multiple compression stages visible, represents the scale of infrastructure required to support these test campaigns. Each component, each system, each facility, all evolving based on real-world failure data. The cryo testing continued at Massey's even during the scrapping operation, frost forming thick on test tanks in the harsh coastal wind. This wasn't optional testing. This was qualifying the next batch of hardware, ensuring that when Booster 19 hits that test stand, it won't repeat Booster 18's failure mode. The wind shaking the camera tower, the frost patterns revealing temperature gradients, the careful monitoring of pressure and temperature, it's all part of the qualification process that turns failure data into flight-ready hardware. Booster 18's catastrophic unzipping wasn't the end of a story. It was the beginning of better engineering. Those petal-like tears in stainless steel, the exposed COPV, the root failure point at the base, every detail is now being decoded into design improvements already flowing into Booster 19 and beyond. SpaceX's willingness to scrap a booster worth millions, study every failure point, and immediately apply those lessons is what separates rapid iteration from reckless repetition. While other aerospace programs might halt for months after such a dramatic structural failure, Starbase keeps building, keeps testing, keeps pushing the boundaries of what's physically possible with steel and fire. The real revelation here isn't just how Booster 18 failed, it's what SpaceX does with that failure. The simultaneous destruction of Booster 18 and construction of the Gigabay, the preparation of Booster 19 while analyzing what killed its predecessor, the infrastructure upgrades informed by real-world failures. This is how you build a spacefaring civilization. Every tear in that steel bought knowledge. Every scrap of twisted metal represents data that makes the next booster stronger, safer, more reliable. The question now isn't whether SpaceX will overcome this setback. They already are. The question is how much faster they'll reach orbit because of what Booster 18 taught them in its final moments. What improvements are hiding in that wreckage that we won't see until Booster 19 or 20 takes flight? Drop your theories in the comments below. Hit that like button if you appreciate SpaceX's transparent approach to failure analysis. Share this with anyone who thinks setbacks mean defeat. Starbase proves otherwise daily. And subscribe to Space Update 24 hours because the next chapter in this story is already being written in steel and flame at the Texas coast. We'll be there to cover every detail.